What's up, everybody? Welcome to the Chapter 14 practice test for CTM. We're going to get right into it here and check out these 12 problems for the graph theory chapter here that we just went through. And make sure you use those extra examples in your book on these pages. Make sure you're ready for that Chapter 14 test coming up. Alright, let's get right into it now and let's work through each one step by step. The answers for some of these, this one being one of those, will not necessarily be exactly looking like what's in the back of the book. This is just a sample answer. What you see in the back, I'm going to try to do my best to actually do an example of something that fits the criteria but does not look like the back of the book. So you can see a couple of different possible answers. You'll probably come up with something totally distinct, but still hopefully where the information is still applicable in your picture. So all that said, create a graph with 7 vertices, a bridge, and a loop. So I'm going to put 7 dots on here, 7 vertices. Doesn't really matter where they go exactly. 4, 5, 6, that's 6, okay, and we'll go with the 7th one there. Okay, 7 vertices, a bridge, and a loop. So a single bridge and a single loop. Why don't I take care of my loop right now? There's my loop. Okay. And it has one bridge, just a single bridge. So that means that I'm going to have all these connected. I guess technically I wouldn't even have to connect them all. It doesn't say it's connected or disconnected. So I want to just have a single bridge, a single loop in here though. I'll make it a connected graph. And it looks like I've done a little too much here, so I'm going to take one of those away because I don't have any bridges if I connect them all like I did here. So I'm going to take this one away, and if I were to do that, then I've got a loop. My loop is right here. This is my loop. And this one would be my bridge, because if I remove that, I then have a disconnected graph. So I guess, yeah, technically this would have to be all connected. If I'm going to have a bridge, it makes it a disconnected graph. Okay, and I think beyond that, let me just double check my vertices. Yep, I got 7 vertices, and so that would be a solid example of what the criteria is for example or for problem 1. So number 2 here, now part of Africa, represent the map below as a graph where each vertex represents a country and each edge represents a common border between the countries. So why don't I just take the map and I'll put in the relatively central locations with respect to each country. I'm going to put a vertex in all these places here. Faso, right, and map each vertex, country, each edge represents a common border, and so the edge here, there's between Benin and Burkina Faso, there's a common border, so I'm going to make connection there, and each edge, I'm going to draw in such a way that each edge crosses over where the actual common border is. There's a common border between these two, there's one between these two, there's one right here. There's definitely one between Ivory Coast and Ghana and Burkina Faso and Ivory Coast, Liberia here, and Sierra Leone right there. And so this would be my graph would look like. There we go. And I'm going to go, this is SL for Sierra Leone, Liberia right there, Ivory Coast. Go with IC, Ghana, Togo, Benin, Burkina Faso. Okay. And it looks like that's all I have to do. And so if you look at the book, it has a similar looking thing, but it uses all straight lines, and I just drew it right on top of the graph and slid the graph, or the map over, not the graph, but the map, and it looks the same there. So the way the book has it looks slightly different, but it's an equivalent statement or an equivalent graph to what I have right here. So a couple different ways to represent that. Okay, now Number 3, lots of different ways you could draw a disconnected graph. I could just do something like this. I'm going to make it real simple. So these two are connected, but then these two are connected. But this is all one graph. I'm saying that's disconnected because there's no connection, no way to get from these two vertices to either of these two vertices. There's no path to follow. In the book, you'll see another example there if you want to check that out. Hopefully that should be pretty easy to do. Number 4, following graph, determine an Euler path. So an Euler path, remember, if it's an Euler path, it has to cross each edge, or go over each edge. So it has to go, we're going to do that in red. These little notations that I'm making. Euler path has to go over is really not a technical phrase, but go over each edge. Each edge gets used. And so I'm going to use my highlighter for this and see what I can come up with. And so an Euler path, if it's a path, it doesn't have to start and end at the same vertex. That would be an Euler circuit, but I do have to go over each edge if this is going to be a possibility. And so something we need to remember from before is that you got to start and end at an odd vertex if any odd vertices exist. This one's even because it has 2. This one's even because it has 1, 2, 3, 4 edges coming out of it. This one's even as well. This one's odd, and so is this one. So I got to start and end at either D or E. So I'm going to go this way, and I'm going to go this way, and I'm going to go this way, and then this way, this way, this way, and this way. That would work out. So I'm going to just put arrows on what I just did. I went from D to A. That's one possible way to go. This would be my first one. I went from A to B. That's the second one. Here ended up being my third one, fourth one, fifth one, sixth one, and seventh one. I think that took care of all of them. 1, 2, 3, 4, 5, 6, 7. Yeah, so this is an Euler path. That Euler path starting at D, so I have D, A, B, D to E to B to C to E. And so that is one possibility. It looks like I picked a slightly different way than the book had. They went from D to A to B to C to E to B to D back to E. So that's another possibility, but this is the one I saw. So this is a sample answer. This is not the only possibility, but you do have to start at either D or E, and you have to end at the opposite one, either D or E. Whichever one you did not start at is the one you're going to have to finish at. That was something we learned about the Euler paths and Euler's theorem. Okay, moving on to number 5. Is it possible for a person to walk through each doorway in the house whose floor plan is shown below without using any of the doorways twice? If so, indicate which room the person may start, and where he or she will end. And so there might be some different possibilities here. I'm going to represent each one of these with each room with a vertex again. And then each doorway now represents a possible way to go in and out. So I could go from here to there, out that way. Each doorway is kind of like the common border that I had back in example or in number 2. So it's kind of like that. But I could go from A to C. I could go through that way. I could go from C to D. I could go from D to A. I could go from D to B. I could go from D to E. I could go from E to B. So it looks like those are all different possibilities there. And just label these again. This is A, B, C, D, E, no F, no G. And each edge here, let's see, did I leave any out? Nope, I think I got them. Alright, so I'm looking for odd vertices. This one's even. It's got 2. This one's 1, 2, 3, 4. That one's even. This one's even. 1, 2, 3, 4. Looks like that's even. 1, 2, 3, 4. It looks like they're all even vertices. And so because of Euler's theorem, we know that you could start anywhere with all even vertices. And is it possible? So number 5, is this possible? Yes, I would say it's definitely possible. If so, indicate which room the person may start. So I would say since all vertices are even, the person may start in any room and will end in that same room. So whatever room they start in, they're going to end in that room. Euler's theorem told us that if you have all even vertices, you can start at any even vertex and you'll end right back where you started if you do this correctly, in that same room. Okay, so let's just, for argument's sake, show one possibility. This I'm just going to highlight. I'm not going to number stuff and list the path. It doesn't say we have to do that. But let's say I started at A. I could go from A to C to D. I could do this. I could go there, 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 and I could go around outside, back this way, and boom, I end up back where I started at vertex A, or in room A. We'll move on though. Number 6, using Fleury's algorithm. Use Fleury's algorithm to determine an Euler circuit. So now an Euler circuit, not an Euler path. This means we use each edge and we have to start and end at the same vertex. Still got congestion. This has been a rough chapter for me making these videos. Just hacking all over the place. Anyway, let's try to finish this up here. So in the following graph, alright, so we have any odd vertices. Let's see, this is 4, even, 4, even, 1, 2, 3, 4, 5, 6, still even, and even. They're all even. So by Euler's theorem, we can start anywhere, and wherever we start is where we're going to stop. There are going to be a lot of different possibilities here. Why don't I start with, we'll make it interesting. We'll start at F down here. I'm going to go F to H to, I think with this one being so many of them, I'm going to use the arrows as I go. Just going to put a little arrow on each one and call that 1, I'll call that 2. So any edge that has an arrow on it means I've already used that and I can't go back to that. Can't go over that one again, so that's 3. Let's see, I could go this way, that'd be fine. 4, 5, and 6. I'm going to go up this way, 7. This would be 8, 9, 10, 11, 12, 13, 14, and so that would bring me to here, back to F15. So we'd have 15 different edges right there that we're going to go across. And let me just put them in the order that I went in. So this is a sample answer. This is not the only answer. Your book has a different possibility. And you might come up with a different possibility yourself as well. So this is one way, one way that will work. This would be F to H to E, back to F. I'm just listing them in the order that I put the numbers on there. So back to F to G to I, back to F again, to B, to G, to C, back to B, to A, to B, to E, to A, and finally back to F. So let's see if I got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yep, there should be 16 letters since I have 15 edges. The edges would connect each of those. And so this is one possibility for number 6. Another possibility in the book, and you probably came up with another possibility if you did that one before looking at the video. Number 7 now, determine a Hamilton circuit. It's different than an Euler circuit. Remember, a Hamilton circuit in the following graph. So here we have to use each, now instead of edge, it's each vertex. Only once. And start and end at the same vertex. So let's find somewhere to start here. I'm going to use my highlighter again. And just wanted to remind you that with Hamilton circuits, there's no nice theorem that tells us, okay, you need to start at an odd vertex and go this way. We kind of just have to do a little trial and error here. But if it's a complete graph, there is a Hamilton circuit. So this is not a complete graph because not each vertex is connected to each other vertex. So we can't assume that there would be a Hamilton circuit, but it says to determine one, so I'm going to take that, and I would say that implies that there is going to be one. So let's try to figure out what one would be. So let's say I start at A, I go to E, and I just keep going around. So I can only touch each vertex once, and I have to end back where I started. So if I went this way, that would not be good, because then I would have to either go to A or C, but there's no way to get back to A. If I close it off, then I didn't create a whole circuit. If I go this way, there's no way to get back to A without touching one of the vertices again. So I'm just going to go around the outside. It looks like that's probably my best option here. And boom, there I go. I'm back to where I started. Notice each edge didn't have to be used up, just each vertex. And I can only touch each vertex once. And I've got a possibility there. So this is a sample answer for number 7. This is not the only way. I believe your book has another way. Yes, it does. It went the opposite way of what I did. So it started this way and went around this way, but I'm going this way in the other direction. So A, E, F, G, J, K, L, I, H, D, C, B, and back to A. So this is a sample answer. Hamilton circuit, not an Euler circuit, so we're using each vertex exactly once. Number 8. I swear I did not make this book. This is awesome. Michigan, my home state. We're going back to Michigan for this one. Okay, job interviews. Tracy Harrison lives in Muskegon, Michigan, and has job interviews in the following other Michigan cities: Battle Creek, Bay City, Flint, Grand Rapids, G-Rap, what? Kazoo, Kalamazoo, Marquette, and Saginaw. How many different ways can Tracy visit each city and return to her home in Muskegon? Alright, there's a place called Michigan's Adventure in Muskegon. It's kind of like the poor man's version of Six Flags or Cedar Point, but still fun. If you don't know what Six Flags is, shame on you. If you don't know what Cedar Point is, shame on you. Two of the best amusement parks in the country, for sure. At least the Six Flags out here in California is pretty sweet. So is Cedar Point in Ohio. Pretty amazing. But anyways, I'm talking too much. Tracy Harrison, let me get to the problem now. Lives in Muskegon, Michigan. Has job interviews in the following other Michigan cities. Okay. And so I'm just going to count these up. There's a 1. And she's going to 1, 2, 3, 4, 5, 6, 7 other cities. So she's starting in Muskegon. This is just kind of me getting an idea. And we've got these other cities: 1, 2, 3, 4, 5, 6, 7. This is not the approximate location of these cities by any means. But she has basically 7 choices at first. And then if she picks one, then she's got 6 other choices she could go to. And then 5 and then 4. This is just a matter of doing 7 factorial because she has 7 cities to choose from here. So 7 factorial, you work that out either mentally by hand or on a calculator. Either way, any way you do that, you get 5,040 ways. Okay, so 7 factorial, that is the number of ways she could visit the different cities. We're not saying which one of these ways is best or fastest or most efficient or cheapest. We're just saying this is how many ways there are. we will probably get to that. Yep, it looks like in this question we'll talk more about what would be cheapest and whatnot. Okay, so job interviews. Number 9, Kate Kozak lives in Indianapolis, Indiana, and has job interviews in Pensacola, Florida, El Paso, Texas, and Albuquerque, New Mexico. The one-way flights between these 4 cities are as follows: Indianapolis to Pensacola, 449, to El Paso, 201, Albuquerque, 203, Pensacola, 728, and so on and so forth. Okay, represent this traveling salesman problem with a complete weighted graph showing the prices of flights on the appropriate edges. So let's do that right here. Indianapolis is kind of over there-ish, and so I'm going to put these in their approximate locations. El Paso would be kind of like down here. Albuquerque would be a little bit farther west, if I got my geography right, and Pensacola, that's going to be Florida, kind of down there. And so let's call this Indianapolis, Pensacola, El Paso, and Albuquerque. We'll just use those letters to represent those. And so we've got the one-way flight prices from each city to each other city because it's a complete weighted graph here. And so I need to make connections between every single city. Have I done that here? It looks like I have, I believe. Yep, there's connections. There's an edge connecting each one there. And now we're going to give this graph some weights, some values. Indianapolis, Pensacola, $449 right there, $449. Indianapolis to El Paso, $201. Indianapolis to Albuquerque, $203. Pensacola to El Paso says is $728. I don't know why it would be that much more, but anyways, we'll just take the numbers that are here. And Pensacola to Albuquerque, $677. And there should be an Albuquerque to El Paso. They're pretty close to each other. $49. That's it. It's a cheap flight right there. Okay, and that's part A. All good? Yep, all good. So part B, use the brute force method to determine the least expensive route. And so there's going to be 3 factorial different ways to go, because I could start at Indianapolis. I need to end back at Indianapolis because that's where Kate Kozak lives here. That's where she needs to end back up. So she's starting here. She's got 3 choices at first, and then she'll have 2 choices there, and then 1 choice to go back to Indianapolis. So it's 3 factorial. There's going to be 6 possibilities here. And let's split that up like this. Okay, so we've got, this is one possibility, I. Could start at I. This is I'll say this is the route. This would be flight 1. Flight number 1. Flight number 2. Flight number 3. And flight number 4. It looks like this one is going to take some time. It's not hard math. It's just a little tedious. This will be the total cost right here. And so let's find each route. There's supposed to be 6 of them. There's 3 factorial, or 6 different possibilities, 6 different ways to go. So we could do I to P to E to A back to I. That's one possibility. We could go I to P to A to E back to I. That's another possibility. We always have to start with I because we're starting in Indianapolis. Then we could do El Paso, Albuquerque, Pensacola, Indianapolis. We could do El Paso, Pensacola, Albuquerque, Indianapolis. And we could, I haven't gone to Albuquerque first yet, so that's a possibility. So Albuquerque, El Paso, Pensacola, Indianapolis, or Indianapolis, Albuquerque, Pensacola, El Paso, Indianapolis. And so I would say that just came across, or that just went through my mind, that this would be pretty dumb, I think, to go from Indianapolis to Albuquerque, fly all the way back to Pensacola, and then fly all the way back here when you're so close. So I'm thinking this one's probably not very good. This one would be a lot better. But anyways, let's check out what the flight costs are going to be as I go through this. So I to P first is $449, and then Pensacola to El Paso, 728. Okay, and El Paso to Albuquerque, 49, and then going back home to Indianapolis, 203. We'll work out the total cost after we figure out all this stuff here. Let me draw in some yellow lines just to make it easy to follow my work here, make it easier. I'm flying, I'm on a plane, I am using the black pen again. Okay, I to P, 449, P to A to Albuquerque, 677, and then Albuquerque to El Paso, 49, and finally back home to Indianapolis, 201. That one to me looks cheaper immediately because this one's cheaper, this one's cheaper, so that's going to be a better option than the first one was. Indianapolis to El Paso, 201, to Albuquerque from there, 49, Pensacola from there, 677, and finally back to Indianapolis for 49. So that one seemed to use the same values. Looks like it's just the opposite order of what I did there. Yep. Okay, so Indianapolis to El Paso, 201, Pensacola, 728, to Albuquerque, 677, and back to Indianapolis, Albuquerque, 203. Okay, and let's see what we got here. Indianapolis to Albuquerque, 203, to El Paso, 49, to Pensacola, 728, and back to Indianapolis, 449, and then finally last one here, Indianapolis to Albuquerque, 203, to Pensacola, 677, to El Paso, 201, and oh, I messed that up. Let's see. I to A to P, 677, to El Paso, 728, sorry, and then finally back to Indianapolis from El Paso would be 201. So at this point I'm just going to double check my work. I'm going to do all the calculations. I don't feel like you need to watch me type these into a calculator, and you can just verify that you get the same thing as me over here. Okay, so I've got all my total costs here, and it should match up like this, where two of the prices are the same. For each value, you're going to have a pair of those because one is just in one direction, the other one that matches up with that will be that same route, just going in the opposite direction. And so I noticed from here, these are my cheapest costs. I'm going to box that in right here. This is my answer, and these are my possible routes. So right here, this would be the cheapest. These are the possible routes right here. Possible routes, possible cheapest routes, and the cost going the cheapest way right there. And then finally, let's do the nearest neighbor method. So choice C, or part C. Nearest neighbor method, you're supposed to start at a certain vertex, which would be Indianapolis in this case, because she's starting and ending there. What's the cost for this route? So I'm going to draw this, I'm going to highlight over here, up here. So the cheapest way to go from here to any of these other cities would be from I to E. The nearest neighbor method would say to do that first, to pick the cheapest or shortest or smallest number first, and from there continue to do the same thing. And so we've already made a connection back to I. I don't want to go back there until I'm all done, until I've visited each vertex. So I would definitely go there next, because that's the next cheapest, either of this one or this one. and then from there I would go this way, and finally I have to go back to I. Now I've touched every vertex, I've visited every city, and that would be the last way there. So this one ends up being, or giving you the cheapest way, the brute force method and the nearest neighbor method. It doesn't always work that way. Brute force is always the best way to go if it's reasonable time-wise to try to figure it out. Remember, we have those supercomputers that if you get too big, if you got too many possible routes, which remember you figured out the possible routes with the factorial idea, the n minus 1 factorial, number of vertices minus 1 factorial. If it gets too big, which happens pretty quickly, then a computer can't even do it in a reasonable time. You have to use something like the nearest neighbor method. Excuse me. My voice is still shaky from being sick. But anyways, what was that? That was I to E, there we go, to El Paso, to Albuquerque, to Pensacola, back to Indianapolis. That was at the same. I'm not going to do that work again. I've already done that work right here. That was at $1,376. Okay. Number 10. Determine a spanning tree for the graph shown below. So I'm going to just redraw the whole thing. And I'm going to use a different color for that so that I can tell what I've done already. So I'm going to draw all the vertices again. And I'm going to be using an eraser to erase things until I have an actual spanning tree, or have an actual tree where each edge is a bridge. Remember, we have to have each edge being a bridge in a tree. And so I'm going to make all the connections that I see here. Just tracing over everything. This reminds me a little bit of maybe where you were in elementary school. They had the handwriting lessons where you had to write in between the lines, and this kind of reminds me of that a little bit. Anyway, number 10. This is number 10. It almost looks like could be music stuff too, but it's not quite, not really. I'll stop talking about non-math related things now. And oh yeah, I want to draw on the vertices too. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, no N, L, M. Okay, eraser time. So I need to remove edges until I have each edge being a bridge. There are going to be different possibilities here, lots of different possibilities, so I will write down that this is just one sample answer. Check out your book for another possible answer. I'm going to erase this one and this one. Now this one and this one are both bridges, so I'm not going to get rid of those. Oh, why not get rid of this one? That's fine. And I'm going to get rid of this one and this one. And I'll get rid of this one. Sure, that'll work. So now this is a bridge, this is a bridge, so is that. That is a bridge as well. Let's get rid of that one. You can do your own spanning tree here. It doesn't have to look like mine. Get rid of that one, and that one is gonna do it for us? I think so. That would be a possibility. Okay, so now each edge is a bridge. If I get rid of any other edges, I would have a disconnected graph. I would have at least one vertex hanging out there saying, "Hey, you forgot about me, guys. There's no way to get back to me anymore." Like this. If I erase that poor D, it's all by itself. Can't do that. If I erased this, there's no way to get from this part of the graph to this part of the graph anymore. Can't do that. So this is one possibility. Your book has another, and you can probably come up with a lot more yourself too. Number 11. Let's check this out and see what we got. Determine the minimum cost spanning tree. Okay, so minimum cost, there's just one, there's not different ways to do this. It's not like the brute force method or the nearest neighbor method where there's all these different possibilities potentially. There is one, there's just one, the minimum cost spanning tree, the following weighted graph. So we have to find the edge with the least value or the smallest value and go from there. And so I noticed that that's going to be, I'll just highlight over stuff, that's going to be this one. And so from there we need to pick the value that does not, or we need to pick the next edge, sorry, I'm thinking about something else, but we need to find the edge that is the smallest that does not create a circuit with any of the previously selected edges. And so I've got 1, 3 would be the next one, next biggest one from what I see here. And as I do this, why don't I give them numbers of what I did first, second, and third, and so on. And so that's there, that's good. 5 would be next. That doesn't make a circuit, so that would be the correct one to select next. That's going to be the third one. These colored values are just the order I went in. The numbers here is what I'm really most concerned with, though, the values themselves. So 5, that was next, and then I would go to 7. I still don't have any circuits by doing that, so that would be okay value to go from there. Alright, next up I got 7, 8, yep, I would want to pick this one because that doesn't make a circuit yet. So it's 5th. Okay. Got 8, looks like 11 would be the next one and still doesn't make any circuits, so that would be a good choice right there, or the choice I would have to make. And then 14 would be next. So that was the 7th choice I made. But then here, 17 would be the next highest value, but that would make a circuit. So I'm not going to pick that one. I've already got all these connected together. No reason to make another connection there. That would just be a waste of money if you were putting in phone lines or fiber optic lines or sprinkling systems or whatever kind of problem might apply to this type of situation or type of graph. Let's see what else we got here. So 19, that would come next. Yep. And that was 8th. And then finally, well, not finally yet. I still have a couple more to do. This 21 would be next. Still doesn't make a circuit. So that would be good. A good next choice. That'd be number 9. And it looks like this would be the last one, number 10. And then that one, 31, it's both the highest, and it doesn't make sense to connect that one instead of that one because this is a smaller value here. So that would be the 10th one. And it looks like I've got all my vertices connected now. And looks like that's good to go. And so that is going to be the minimum cost spanning tree. And so if we were to draw this over again, I think that'd be a good idea for this one. What does the actual tree look like in the end? I'm going to redraw my vertices. Give them labels again. Just trying my best to make regular hexagons. But then the connections are just the ones I have highlighted up there. I'm not going to connect here to here, and I'm not going to connect from A to E either. A, B. You're going to sing again. C, D, E, F, G, H, I, J, and K. And this is 11, 14, 1, 8, 5. This is 19, 21, 3, 7, and 24. And there are not other possible answers. This is the answer for this one. It doesn't say you need to find the total value of all these, but all we would have to do with that is just add them all together, and that would give me what that would be right there. Okay, so we don't need to actually do that though. Let's move on to the last one. So we have this irrigation system. Daniel Borowitz is planning a new irrigation system for his yard. His current system has valves already in place as shown in the figure on the right, and the numbers shown are in feet. So we got to determine the minimum cost spanning tree that reaches each valve. And so here's my different valves. I'm going to put I use a different color again so that stand out a little bit better. Okay, I've got right here my different valves are going to be my vertices, and I need to make sure that they're all connected, but connecting them twice or 3 times doesn't make any sense. You're just spending more money that you don't need to spend. We just need to make sure they're all connected at least in one way, or only in one way, to wherever the water source is coming from. I'm going to say that's out here somewhere. I don't know. It doesn't show where the water source is coming from, but we're going to assume that each one of these valves is somehow connected to the water already, I guess. Anyways, stop talking so much, Mr. Wagner. Gotcha. Okay, number 12 part A. Determine the minimum cost spanning tree that reaches each valve. And so we're looking for the lowest cost first, and that's going to be right here. This is the lowest cost right there. That's 29. And I'm going to call this V1, valve 1, valve 2, V3, valve 3, valve 4, and valve 5. So that's first. And then do the same idea as what I was doing here. I'm going to cross off any if they make a circuit, and I'm just going in order from smallest to largest numbers. And it looks like 32 is next right here, so I'll trace over that. 32. What looks like the next highest value looks like 41 comes next. So all I need to do now is make a connection here between V1 and one of these other ones somehow. It looks like that'll do it right here. The next highest value is actually going to connect me to V1. So all these other values, could I make a connection here and here? Sure, but what's the point? Why are you going to do that? Why are you going to waste more money connecting something that's already been connected to the rest of these? And so this would be the minimum cost spanning tree that reaches each valve right there. Ooh, fancy. So this is part A for number 12. Part A, this is the picture you need. That's all you need. And so part B now, to put a little perspective on this, or to make this a problem worth doing in the first place, if new irrigation materials cost $1.25 per foot, find the cost of installing the system determined in part A. So the whole reason for doing something like this is to do this as cheaply as possible. And so now we've got all these values here. This is going to be the total feet. Just add these values on the spanning tree together. 29 plus 32 plus 41 plus 45. Let's see what that gives me. Yes, I want to open the calculator. There we go. 29 plus 32 plus 41 plus 45. 147. So the total number of feet is 147 feet. And now it's $1.25 per foot. So the total cost, I would just take 147, multiply it by the 1.25, $1.25 per foot there. So take that times 1.25, and I get $183.75. Somebody that didn't know graph theory or didn't think of this, they might have spent 98 times $1.25. They might have spent that much trying to connect these ones, and they would have gone to a Lowe's, Home Depot, place like that, spent more money than they needed to, while you're enjoying a nice dinner on the grill, paid for by the amount of money you saved on not making poor connections or more expensive connections than you needed to. Nice job. Enjoy your meal. Enjoy that grilled chicken, whatever you got. So I think that'll do it for us. There's no more questions. That's the end of the chapter review. Don't forget to use those extra examples if you need some more practice still. Check out the chapter 14 review in your books. Hopefully do well on the tests, and I'll see you guys later.